So let's move to the next talk. It's going to be again online. It's being Christian Adam from CITEBA, Centro de Astronomía de la Universidad de Antofagasta, and he will be explaining us estimating the impact to astronomy from the OneWeb satellite constellation using multicolor observations. So whenever you are ready, Christian, the screen is yours.
Hello, yeah, can you hear me?
Yes.
Yeah, and can you see my screen?
Yes.
Yeah, okay, I will scroll to them. So yeah, thank you very much for the invitation to talk. Unfortunately, I cannot be there in person, but I will try to do my best to present our project, which is about estimating the impact of OneWeb satellite constellations, in particular with multicolor observations. And yeah, we have already heard in the talks before and yesterday that the importance to observe the satellite constellations. And just to give a small reminder, so these are the satellites within 2,000 kilometers, and we have heard of Starlink, the OneWeb, and the Blue Walker satellite, and there are a lot of more satellites to come. And these satellites provide some pros, which are, for example, here in Chile or in other countries, very prolific. So they provide high-speed internet to rural regions, and this facilitates the development, the economic and educational opportunities in this part. But we have also already seen that they are producing a lot of problems, which we have to address. So their large number, their high reflectiveness over a large wavelength range in the radio and in the visible. So we have to know what is their impact on astronomy, and therefore we need to collect data in multiple wavelengths and analyze them from different locations all over the world. As we recently heard in the last talk, the locations of the satellites have a great impact, or the observation location. So for this purpose, we have founded, so Jeremy, Trigger, Reed, and others in Chile here, we have founded the ClearSat network, which is comprised of telescopes in Chile, of course, and also from other countries. So like from Mexico, Spain, and in South Korea and Vietnam. And maybe you recognize the Jacana 0.6 meter telescope, which is also recently used to observe the Blue Walker satellite as part of the ClearSat network, and our effort to study satellites from all over the world. So for our particular study of the OneWeb satellites, we have used the Danish telescope, which offers a 13 by 13 arc-minute field of view and a set of filters in the B, V, R, and I range, so we can observe multiple wavelengths at the same for this satellite. The telescope is operated jointly by the Danish and Czech astronomical communities, and the data I will present here were taken from the Mindset Consortium in the years 21 and 22. They also did some observations of Starlink satellites along this. So the OneWeb satellites, so yeah, the number is increasing. So the last number I found was 648 satellites currently, but I think they maybe already had launched more. They fly, the nominal orbit is about 1,200 kilometers, and they are 1 by 1 meter boxes, more or less, with panels attached. So the observations we have analyzed were taken in 2021 and 2022. And as you can see, consists of 50 V-band, 100 V-band, 90 R, and 130 about I-band observations. In total, we have 369 successful detections of 100 different individual satellites, 159. And the goal of our observations primarily was to quantify and model the brightness of this in relation to their phase angle and the sun satellite observer geometry. On the right side, so just to show you, these are the example, and due to the large exposure time, we only have the full trail of the satellite in the image. So the next task is, of course, as we have seen in the other talks, to extract the satellite trail information. And for this, we have developed a fully automatic pipeline which is from end to end able for the telescope in our ClearSat group to process the data. So it consists of the image processing, the detection, and the tray analysis. So we first calibrate the image astrometrically and correct the image. Then we use image segmentation and the U-transform to find the satellite trail. And when we have detected the satellite trail, we can extract the brightness information, and with the use of TLEs, we can also get the sun satellite observer geometry. So, and to maybe just show this a little bit more detail, we have the detection of the satellite, which is after pre-processing of the image. We use a segmentation algorithm, which produces the segmented image, which we then clean and convert into a binary image, which allows us to apply a U-transform. So U-transform is used in computer vision to detect lines or line segments, and using a special, by transforming the line or the points of a line into a parameter space defined by the distance and the angle. So like polar coordinates. This approach, U-transform itself, only works for infinitely thin lines. So in order to detect the satellite trail, which is extended, which is more than 1 pixel wide, we use an approach by XUSL, which allows us to extract information from the accumulator array, so from the voting array, and by applying a linear fit and a quadratic fit, we are able to measure the position, the center of the trail, as well as its length and its width and orientation in the image. Once we have the trail identified, we can then perform photometry on the satellite trail. So we use aperture photometry and first determine the optimal signal-to-noise ratio. Then we apply aperture correction to account for the finite aperture and get the observed magnitude of the satellite. We can then correct, since the satellite is not only a few, so it's less than a second mostly on a detector, depending on the velocity. We have to correct for the velocity for this, and this gives us the estimated magnitude. And for comparison, we then normalize the satellite magnitudes also to a reference height, which is the orbit height of this OneWeb satellite of 1,200 kilometers. So, and on the right side, for example, you can see an example of what our pipeline produces. You can see the satellite trail as well as the aperture measured, and the blue line, the blue line shows the predicted path from the TLE. So we can see discrepancies in the position and timing of the TLE. Yeah. So what did we find now? That as shown here, these are the results of our measurements. And first we have the observed satellites and our observed magnitudes. It's over the 4 bands we have analyzed, we can clearly see an increase in the magnitude, whereas the general magnitude is between 7 and 10th magnitude, depending on the band. But it's also very clear that there's a large variation of almost the magnitude in the data, which is also reflected in the magnitudes which are corrected for range. On the left side, you can see the color indices compared to the solar color indices, which also indicate that there's some specular reflection going on. Does not reflect the solar. Yeah. In the last talk, we have also introduced the effective albedo, which produce the effective light, which shows the which shows the brightness for unity sphere, the effective albedo for unity area. And in this data, it becomes clear that the effective albedo is increasing with the reflective brightness and for larger angles. So yeah, along the we also tried, as we have also tried to apply models to our observations. One is a mixture of a diffuse specular sphere model from Balaran, and the other one is a diffuse sphere model from Gole. And they use the effective area, which is the albedo times the area of the satellite, as a measure, as well as a component which allows for the mixture of specular and diffuse reflections. So if the beta is 0, then we have diffuse reflections, and if it's 1, then we have, if it's 0, we have specular reflections. If it's 1, then we have diffuse reflections. So from our data, we can see that the effective area of the which reflects light is increasing with wavelength. So the general trend is visible, but the data clearly cannot account for the observations. This is mostly, as mentioned in the previous talk, because of the orientation of the satellite, and we have much more work to do in order to account for this. So to summarize, so what our data so far show is a clear increase of the brightness towards the redder bands, and the color indices clearly deviate from the solar wavelength, from the solar values, which indicates the wavelength dependent reflections and absorption properties of the materials. We also find an increase in effective albedo with increasing phase angle and effective brightness. But in general, only as one quarter of the observed satellites are brighter than the magnitude limit of 7.8. So we can find the general trend in the models, but we cannot account for the whole picture. So clearly the satellite geometry and orientation attitude have a much bigger impact on the observed brightness than previously assumed, and we have to do much more work to account for this. For example, using spectroscopic observations, which allow us to better differentiate or to better assess the material properties at different wavelengths, which are not always provided by the satellite manufacturer. We also should track the observations and tracking of individual satellites in different passbands to better constrain and model, to better constrain the geometry and attitude of different phase angle. And of course, improve modeling. So we have to improve our modeling to get better brightness forecasting with updated data. With this, I would like to thank you very much. I'm happy to answer questions.
So, thanks a lot, Christian, for a nice presentation. We do have a question from the online audience, Olivier Henault. How faint in terms of signal-noise ratio can your method with the half transform detect the trails? Does it work for super faint trails?
I've designed to work with as faint as possible. So it should work around 1 to 2 sigma above background. 1 sigma is very rough, but I can make it work with a little bit more, like 2 sigma above the background.
Okay, thanks. Any other questions? Actually, I do have one. So you have mentioned that most probably the brightness will vary. I mean, the attitude of the satellite will impact on the brightness. And are you trying to assess or model the attitude of the spacecraft with the variation of the brightness in the light curve that you're acquiring? Or is within your plans, basically?
It is one of the plans. So we would like to track individual satellites and then construct maybe a light curve depending on the phase angles, depending on the position of the sky. So we can really see what the geometry of during the observation, how the changes in geometry affect the brightness.
Okay, thanks.